we have to take a deeper look at what it means to go into a combinational block and break it down for pipelining. We are starting out with this logic function f, which is a rather large logic function. We have made a couple of assumptions. First, that input complements are available without additional inverters. And second, that there's no loading from any register that we put on a logic gate, so that registers do not offer external loading on preceding logic gates. We will also assume that T-setup and T-seq are 0, just for the sake of simplicity. And whenever we talk about delay, we will only calculate the time constant as a representative of delay. So we have an option about implementing f as a single logic gate. Not going to draw this logic gate because it's going to be huge, but it's simple to imagine. It will contain two long chains in the pull-down network, two long NMOS chains in the pull-down network. Each will have 6 transistors in the chain, and it will consist of 2 blocks in series with each other in the pull-up network, each consisting of 6 PMOS transistors in parallel. If we size for resistance equal to the unit inverter, we will have a total self-loading at the output of F, which consists of 12 C0 from the pull-down network. 6 C0 is contributed by each NMOS transistor, because we have 2 NMOS transistors with drains connected to the output, each of them lying in a chain of 6 transistors. In the pull-up network, we have 2 PMOS transistors at most on the way to the supply, so each PMOS transistor is going to be sized at 4, but we have 6 of them along the way, and so we have 24 C0 coming from the pull-up network, in which case we have 36 C0 as total loading capacitance. All of it is intrinsic. And the time constant for this gate will be 36 R0 C0. Now, if this is not acceptable, we can break down this logic function into 3 logic gates. The first is F1 is equal to AB, C, D, E, G, and F2 is equal to H, J, K, L, M, N. And then these two are brought together in a 2-input NOR gate to give us F. So this is the simplest way we have to break down this logic. And let's first assume that there are registers only at the inputs, the very first inputs and the very last outputs from the circuit. And let's calculate the total time constant from the input to the output in this case. And this is assuming that the critical path goes through either F1 and F or F2 and F, because F1 and F2 are both the same kind of gate that is. Now F1 and F2 are going to be 6-input NOR gates. So the resistance, if we assume we are sizing for resistance equal to the unit inverter, the resistance is going to be R0, but the self-loading and external loading capacitance have to be calculated, and so resistance is R0, but we have a 6-input NOR, which gives us a 6 NMOS transistors in the pull-down network connected to the output node, imposing 6 C0, and we have a single PMOS transistor in the pull-up network, but that single PMOS transistor is sized at a size of 12, so we have 12 C0, and this is the internal or intrinsic loading from the gate F1. The gate F2 is going to be a 2-input NOR, imposing a loading of 5 C0 on each of F1 and F2, of which 1 comes from the pull-down network and 4 come from the pull-up network. So the total capacitance then is 23, and the time constant is 23 R0 C0. So for gate F, the output is not loaded. It is only self-loading that we observe, and so the time constant for gate F is going to be, we have 2 NMOS transistors in the pull-down network and a single PMOS transistor sized at 4 in the pull-up network, and so we have a time constant of 6 R0 C0. The total time constant for this network then is 29 R0 C0, which is an improvement over the 36 R0 C0, but maybe not as much of an improvement as we had wished for. So what we can do is we can go and insert internal pipelining registers between each of these two blocks to cut the critical path. So what is the new critical path? We have to calculate the time constants. For F, the time constant will still remain at 6R0 C0, but we have to go and recalculate the time constants for F1 and F2 because now they are not loaded by the gate F. So their time constants will change. These gates had a time constant of 23R0 C0, of which 5R0 C0 came from external loading, and so their intrinsic delay is 18R0 C0. So notice that when we talked about the assumptions in the beginning, we assumed that there is no loading from registers, and so now gates F1 and F2 are not externally loaded. The new critical path now passes through either F1 and F2, and our new total time constant is 18R0 C0. So it is an improvement over the 36R0 C0. It is an improvement over the 23R0 C0, over the 29R0 C0. But what if we still don't like this? What if we still want to see a further improvement? We can go down into F1 and F2 and break them up. They are single CMOS gates, that is true, but that doesn't mean that we cannot break them up. In fact, let's do that. So we have now 4 gates in the initial stage. Gate F11 is going to produce ABC all bar. So we have 3 input NANDs in the first gates. So all of these are going to have to produce 3 input NANDs. And then these 3 input NANDs are going to be combined. So we produce F1 as F11 plus F12 bar. So these are 2 input NORs, right? And so forth. So for these 2 guys, they're going to be combined into F2, which is F21 plus F22 bar. And then finally, we can combine these into F. The final F is equal to F1 plus F2 all bar, right? So this is F. And so now we can first assume that there is pipelining on the inputs and outputs. But we know that eventually we are going to do full internal pipelining because that's why we broke down F1 and F2 in the first place. And so let's just do that and try to find out the new critical path and the new time constant. So the new critical path is going to be the longest of any of these gates, right? And so we have 3 types of gates. We have the gates for the 3 input NANDs in the beginning, and the 3 input NANDs are going to have a resistance of R0 and a capacitance that comes from a chain of 3 NMOSs in the pull down and 3 PMOSs connected to the output. So there will be 3 C0 from the NMOS and 3 C0 from and 6 C0 from the 3 connected NMOSs in the pull up. So it will be 9R0 C0 for all gates F11 through F22. For these 2 input NORs, on the other hand, we have R0 and we have 2 C0 from the pull-down network and 4 C0 from the PMOSs in the pull-up network. It's just 1 PMOS actually in this case. And so you'll have 6R0 C0. And for the final gate, it's also 6R0 C0 because it is a 2 input NOR. And so now the new critical path is obviously in the first stage of gates, and this will be our total time constant, which is 9R0 C0, which is an improvement over the 18R0 C0 we had here. So the conclusion that we reach is, if we don't like the critical path, we should go in and break it down, even if our path originally only contained a single CMOS gate. That CMOS gate could potentially be broken down into smaller CMOS gates. Now, if you notice, the more pipelining we do, the more stages we have to pass through before we reach the output. So what is that? That is latency. We talked about latency in an earlier video. This is latency, the number of cycles that pass before we observe the first meaningful output. Or if we introduce a certain input, it takes a certain number of cycles till we get the output that belongs to this input. This is also called latency. But after this latency, we will observe an output every clock cycle, and that is called throughput. So the 9R0 C0 that we calculated is related to throughput. Throughput is the number of outputs produced per unit time, and therefore throughput would actually be 1 over the clock period, in which, in this case, the clock period is 0.69 times the combinational delay 9R naught C naught. We do not have a setup time or a CQ because we assume they are 0 in the beginning.